In this video we are going to look at a synoptic style question. Now this theme of question is really common to do with ion propulsion engines. So pause the video now and try out parts of this question. Part A asks for the specific charge of a xenon ion. So the specific charge is the charge per kilogram, per unit of mass. Now if you remember that the units are coulombs per kilogram, right, you'll always remember this formula. So we need to work out the charge. So it's a singly charged ion, so that means it's 1.6 times 10 to the minus 19 coulombs, and the mass is 2.18 times 10 to the minus 25 kilograms. So that's really nice and simple for the first part of the question. Let's put that in our calculator now and figure out the answer. So it's 6.9 times 10 to the 5 coulombs per kilogram. And you should always expect pretty large numbers for specific charges. So the second part asks us to calculate the energy in joules gained by each xenon ion. And it does give us some information about the power of the engine and the mass, but this is not needed. We just need to know what the energy gained is, because it's simply saying, can you convert electron volts to joules? So we need to remember that 1 eV is 1.6 times 10 to the minus 19 joules. So if we've got 1.2 keV, we're just going to scale this up. So 1.2 keV times by 1000 to get it from kilo electron volts to electron volts, times by our conversion factor 1.6 times 10 to the minus 19 joules per electron volt, gives us our energy. So 1200 times 1.6 times 10 to the minus 19 gives us 1.9 times 10 to the minus 16 joules. Determine the length of time the ion propulsion unit can be operated before all of the xenon is used up. And again, it reminds us of the mass of the xenon atom. So this is a clue that it's not as simple as just saying power is energy over time and just using this power and this energy. The reason you can't just use this is because we have 55 kilograms of xenon, and if we just use this equation, we're not taking into account the amount of xenon that we have. So there's two ways to do this, but I think the easiest way is firstly to work out the number of particles we have, and then we can figure out the total energy of these particles and then use this formula. So the number of particles is really easy. 55 kilograms divided by the mass of one particle, which is given to us here. It's also given to us up here as well. So times 10 to the minus 25 kilograms. And this gives us 2.5 times 10 to the 26 particles of xenon. So now we can work out the total energy required to accelerate all of these ions. So we know the energy of 1. So 2.5 times 10 to the 26 times by 1.9 times 10 to the minus 16 joules. So that's going to give us 4.8 times 10 to the 10 joules. And now we know the total energy required. We know the power of the engine. So now we can say that time is energy over power. So 4.8 times 10 to the 10 joules over 1600 watts. Of course it's kilowatts we need to convert. So this should give us our answer, which is 3.0 times 10 to the 7 seconds, which is actually quite a lot of seconds. So let's convert that into hours, convert that into days. That's a year which actually does seem like a huge amount. So it's possible that we've made a mistake. So I would encourage you to double check your answer to make sure you're correct. And then in part D, will helium or xenon ions be better to use? So what we need to recognize here is that the force from the engine is equal to the change in momentum over time, so Newton's second law, and of course change in momentum depends on mass and velocity, because momentum is mass times velocity. So what's going to happen if we use helium? So helium ions have a smaller mass, so less momentum, but a greater velocity, because obviously it's easier to accelerate things with a smaller mass. So the question is, which one of these two factors is going to be greater, and is this change in momentum going to go up or down? So what we should consider is what is going to be the same for both of these. Well, they're both being accelerated through a potential difference, and they both therefore are going to gain the same amount of energy. So they both gain 1.2 keV worth of energy. That is of course going to go into their kinetic energy store, so energy is half mv squared. So what's going to happen? Well, the mass is going to decrease, the energy is the same, so the velocity must increase. Now what's going to have a bigger effect? Well, the velocity will only increase to the square root of the energy. Alright, so for example, if we divide the mass by 2, the velocity is only going to be increased by a factor of √2. So the smaller mass has a far greater effect. So overall, the helium ions result in less force and should not be used, or the xenon ions should be used. So in actual fact, the mark scheme doesn't actually require this little bit down here, it just requires you to say this. But I think this on its own is not helpful, because you might say, well hang on, momentum is mass times velocity, so if I make this smaller and this goes up, well overall the momentum should stay the same. But if we look at it in terms of energy, we can see that the mass has a far greater effect than the velocity.